Test, test, test. 1, 2, 3. I mean, I suppose I could put it to the the coming attractions screen, but, you know, it's gonna be class very shortly anyway, so. Good morning. You guys won't let me down. I could have 2 viewers and you 2 would show up. I love that. I love that dedication to your education. It's really nice to see. You know. Although, you know, well, I don't know. I kind of want to say something like usually we do better than 20% of the people coming to class by the middle of the course. Happy middle of the course, by the way. It's going by fast. It's going by fast. Alright, fancy meat computers. I got one thing to say to you people before we get started. Been getting a lot of invitations to collaborate on special repositories that are set up specifically for Lab 3. If you guys, just please also include those repos inside of your CS1XC3, inside of those repositories, because that's where we're going to look for them to get the marking done. So if it's not in your global submission repository, then it's not going to be marked. So please, if you haven't done so already, take a moment to do that. I'm probably preaching to the choir here, but, you know, whatever. Yeah. Right? These summer courses go by so fast. Absolutely terrifying speed. Yes! We are at warp speed! Warp speed to computers. Uh-oh. Disconnected from chat, but the thing's still coming through. My cable is still plugged in. Everything seems fine. Come on. Can't disconnect me from my chat, guys. My chat bros. Yeah, anyway. So, yeah, overview of the week. We've got a lecture right now on benchmarking and profiling, so we're going to be doing Unix type stuff once again. Tomorrow we're going to talk about pointers in C, and pointers in C are a very conceptually difficult topic. It's also from one perspective, kind of the whole point of teaching you an ancient language like C is so that you can get the lecture on pointers. So, like, if there was a nub, a crux, a fulcrum around which all of the C material, bends like a seesaw. Well, the whole point of a seesaw is that it doesn't bend. Rotate like a seesaw. It is the material on pointers. So, please make a special effort to, be on time for class tomorrow, because we're going to be talking about some pretty interesting stuff. Aside from that, we've got lab exercises this week. The first one is on the subject of benchmarking and profiling, and the second one is... oh, come on. I can't forget that quickly. I was just working... oh, my camera broke again? Labs. Lab 6. What's Lab 6 again? Environment variables and libraries. Ah, yes. Ah, yes, I remember now. The lab tomorrow is on the subject of how to do C libraries. So there's kind of a I bet my microphone went as well. Yeah. There's a thing with people who teach C where they think that if you include a file, that makes it a library. That's actually technically not the case. A file which has merely been included and is being used is not a library. A library is a type of archive, which you have to produce using special mechanisms. I'm going to close my email so I don't get dinged out by my email. And we're going to be exploring that in Lab 6. Everything is very, I give you the commands you need to use, but you might need to use them on a novel situation type thing. You should be used to the way the labs work by now. So, anyway, we can get straight into our lectures for today. We're going to talk about a bunch of stuff. I really have been enjoying putting together the material for this course because it's kind of like a grab bag. It's like, we're going to do a lecture or two, or, half a lecture on like a dozen things in this course. I'm sure you will have noticed this by now. There's no particular connection between the stuff we did on repos and the stuff we did on shell scripting. Except, of course, once you get into actions on GitHub, where you can actually start introducing shell script actions automatically on push or on commit, and that type of thing. So, like, you can actually... like, these things link up quite a lot once you get into them. But, anyway. So we're going to talk a little bit about benchmarking, profiling, and advanced bash commands. That is to say, we're going to talk about how permissions work in Unix, which is important. So, let's get right into it. So, we're going to talk first about viewing processes in HTOP. Then we're going to do benchmarking using time, profiling using gprof, source code annotation using gcov, and file permissions in Unix. These guys here, these are roughly the constituents of lab number 5, which is what you guys will be doing immediately after this lecture. So, talk about cutting it close, eh? Ha! So, what gives people feelings of power? Money, status, and HTOP. It's like Control-Alt-Delete for Linux. It's Control-Shift-Escape now. ... Of course it is. Because Windows can't be happy with anything. Even something that's like an iconic meme like Control-Alt-Delete. I've got the T and the R mixed up there, I see. Anyway, so, HTOP of the morning to ya. Modern operating systems, including all of the ones that you use, manage hundreds, even thousands of concurrently executing processes. They're not being executed all at the same time, but essentially, how it works is your computer has resources and processes that use those resources, right? Resources are things like your CPU and your memory, and processes are the programs that your computer is trying to execute. You can have a very large number of processes currently open, and the computer looks like it's multitasking, but what it's actually doing is it's rapidly moving its resources between these different processes. right? So, the process that displays my mouse pointer on screen doesn't need very much, like, it only needs the CPU, maybe, 1/10,000th of the time, or something like that. The CPU can switch between processes reasonably rapidly, and that's why your computer looks like it can do like 100 million things at once when it's actually just doing one thing at a time very, very quickly. This, of course, starts to break down when we introduce the concept of, multi-core CPUs, right? But, I think are they still on quad-core, or have they gone up to octo-cores? I'm not sure how many cores are standard in an Intel CPU these days. But basically, the number of things that you can do simultaneously is limited. It has a hard cap of the number of CPUs you have, right? But anyway, the programs that your computer is currently operating are known as processes. Each one has a unique process identification number, or PID. One program may spawn separate processes, which are known as threads. So this has become more. Yeah, is it octo now? Yeah, cool. Yeah, that's good. Because that's the only way. Like, that's how we're managing to push forward Moore's law now, is primarily through increasing the number of cores. But anyway, so when you have a program, so that sort of raises another question, right? If you have a program, how is it that the computer knows how to distribute that program over 8 different cores? And as with a lot of things in computing, the operating system is mostly incapable of making those types of decisions. What has to happen in order for a program to actually make use of all of those cores is you as the programmer need to include in it the ability of the program to spawn threads. And a thread is a sub-process, separate process. It's executed and dealt with separately by the CPU, which means it can be put on a different core than the one that the parent process is operating on. But this thread, like, it needs to be essentially sufficiently independent from the main program that you can just sort of give it some input, have it process its stuff, and then receive the output back from it, plug that back into the main program. So you can, how functions work is a reasonable, it's a reasonable approximation for how a thread should work, right? In order to be effective, a thread has to be isolated from the rest of the thing that's operating, so that it can operate, in parallel with little communication with its parent process. But anyway, so process management and scheduling, the type of stuff I've just been talking about, is the subject of such wonderful courses as Computer Science 3SD3 Concurrent Systems and Computer Science 4DC3 Distributed Computing. So if you're interested, if the things I've been saying to you over the last, 30 seconds seem interesting, there are computer science courses you can take where you can learn how to do this kind of stuff. But that's kind of... right now I'm just trying to explain what you're going to see once we invoke HTOP. We can view information about our computer's currently open processes by calling HTOP. Oh, my goodness. Close. Open. HTOP. Ta-da! So this is HTOP. You see we have some lovely little bars going on at the top here. 1, 2, 3, 4. I'm currently on a quad-core machine. So this is the usage rate of each one of my CPUs. This is the usage rate of my core memory. So right now I'm using 5 gigs out of 7.6. You can tell that my computer's a little bit on the old side. It only has 8 gigs of memory. But if you take a look through here, every item in this list in the lower half of HTOP, each one of these is a separate process that's being executed on my computer. So, for example, I should be able to find OBS. Yes, so user bin gnome shell, that's like my operating system stuff, right? So I've got OBS running, quite a few different subthreads. There's Firefox. Firefox I'm using to actually, I'm using Firefox as the sort of, the dock for the streaming that I'm doing right now, because I would use Opera, but Opera doesn't work with some stuff. Firefox, 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 look at all these bloody threads. That's a lot of threads. And you can see that, you can tell they're different threads because each one has its own unique process identification number. Right? So Slack is still open, even though I've closed it, because I'm still receiving notifications. Anyway, you get the idea. So there's just a whole lot, and you know, the stuff at the top here is operating system stuff. But you know, so that's HTOP. Here is a picture of HTOP. If you you know, if you put it into a window instead of the Gwake terminal. Incidentally, if you are on a Linux thing, this program that I'm using to bring up a terminal with a single press of a keyboard button, that's called Gwake. I highly recommend it, because you can, like, I've mapped it to the you know, that button that's useless that brings up like right-click menus that you never use. It even kind of looks like a terminal. But anyway, when I do HTOP, I hardly get any programs running. Does this mean my computer's doing nothing? Well, it depends. If you're doing it within the, if you're doing it inside of the Windows subsystem for Linux, I wouldn't be surprised, because, like, HTOP is probably not going to see all the Windows processes that are going on, right? Windows will be sandboxing you inside of probably a very, very lightweight Linux shell. The other thing to keep in mind is that the distro that I'm running is Ubuntu, and Ubuntu is, shall we say, it's one of the fatter distros. Like, a lot of stuff is included in Ubuntu that, like, you may not necessarily want or need. If you were to go with, like, Xubuntu, it's like Ubuntu but with an X in front. That's made to be a lot more lightweight, so it would have fewer processes that run by default. But yeah, no, it doesn't. It might also be that you're just not expanding all the sub-processes, something like that. I don't know. But yeah. You are using the Windows subsystem. Well, I mean, think about it, right? Like, the Windows subsystem for Linux, it's not like... It's what it's essentially doing is it's taking a very, very lightweight Linux distro that the Windows people have put together, which is, I think, Debian-based, but I could be wrong, and they're sandboxing it, right? So it thinks it's its own operating system, but it's actually just a small program that's emulating an operating system so that you can run a Linux environment. But yeah, HTOP. So HTOP includes many useful things that, it displays many useful things, especially if you're interested in how your programs are running, not just that your programs are running. So you've got % utilization of each CPU core. You've got memory usage out of total memory available. You've got swap space usage. You've got the number of processes and threads currently running. That's right here. So I've got 209 programs running on 950 threads, and currently 2 of them are actually executing. It also tells you how long it's been since you've turned off your computer. So your uptime is the amount of time that your computer has been on. So it'd be interesting to see, like, if Windows shuts down the you would be able to tell if Windows was shutting down the emulator between you opening and closing Windows by how much uptime your Linux distro reports. So for each individual process, we can see the amount of CPU and memory that the process is occupying. You can see, like, if I go back to OBS, it's probably using, yeah. So if you take a look here, OBS is right now occupying between 66 and 75% of my CPU, of the CPU time that's being used, right? That's not a percentage of full CPU capacity, because you can see, like, my cores are running at about 30%, right? No, that's of the stuff that's running on my computer. About 70% or 75% of my CPU traffic right now is attributable to OBS. That's, yeah. Origin within the file system. So you can see where in the file system OBS is, or where it's being called from. You can also see which user is running it. It's Nick, because Nick is me. But you, like, if you scroll through this, some of it is, you know, like root is some of the stuff. Some of it is kernel operations, you know. I'm not sure what all of this means, but yeah. Yes, it is Better Task Manager. It is Better Task Manager. That is precisely what that is. Yeah, that's what HTOP is. It's just Better Task Manager. Because one of the things that you can do with HTOP is you can kill processes. So F9 will kill the process that you're currently on. And that might, like, I'm not going to do it for you, because I need all of the programs I'm running currently. But actually, maybe I could do something here. Let's see. Applications, games, SuperTux. Let's see if I can kill SuperTux. Whoa. All right, it has music. So this is like a Mario-like game, which is you know, it can come with Linux if you want. So let's see if we can kill SuperTux. SuperTux. There we go, SuperTux. And F9 to kill. Enter. And you can see that killed it instantaneously. The annoying part about Task Manager in Windows is once you've sent the kill signal, like, the program still, like basically that's a kill signal to the program with a watchdog timer in the operating system. Like, the operating system allows the program some time to kill itself, and if it doesn't in a certain amount of time, it'll prompt you to say, oh, do you really want to kill this guy? He looks like he's working on something. And it's like, yes, I wouldn't have said kill unless I wanted him dead. So, in comparison to the bureaucratic structure endemic in Windows operating systems, the Linux operating systems basically have a sniper trained on every process that they run, and the moment you tell Linux to kill a process, it's like, are you sure? And it's like, and you're like, yes. Blam! You're dead. Headshot. Anyway. So that's HTOP. HTOP is cool. But it's not, like, HTOP is good, but it's not as good as we need it to be in order to do benchmarking, right? So what is benchmarking? Benchmarking is the practice of measuring a product's features or performance and comparing the results to other products of a similar nature. So, obviously, within the context that we're currently operating in, that is a university course, we're not going to be comparing products, we're going to be comparing algorithms, but algorithms, like the method for comparing an algorithm and a product is reasonably simple, or reasonably similar. That's the assumption underlying your entire education, is that these skills are somehow transferable to the real world. So anyway, benchmarking, the term, derives from the 19th century. A benchmark was a channel cut into a stone in order to mount measuring equipment that they used for surveying land. During the 19th century, there was a great deal of surveying that occurred, particularly, in places like North America, which were being opened up for settlement. In order to start up, like, farms and stuff, it's useful to have a system of roads. And in order to have a system of roads, you have to do surveying of the land. And, if you go to Stony Creek, they have in Stony Creek downtown, they have a statue to the guy who surveyed Stony Creek and, laid out where the roads should be. But anyway, in hardware, benchmarking involves executing batch operations that push the hardware to its limits. I have a friend in the office who loves benchmarking pieces of hardware that he rescues from various points around campus. You just sort of load up your disk, you run all kinds of operations on it, and you read those operations to see how fast the disk is. We can benchmark software as well, though. The reason I tell you that about hardware is, if you Google benchmarking, most of the results you'll get are for hardware benchmarking. In software, we are typically interested in time and memory performance. With HTOP, we can see time and memory for the active processes, but what about programs that take a fraction of a second to execute, right? Anything that you have written that you run in the terminal is going to execute very, very, very quickly. It's not like OBS. It's not like a continuously running program, right? So what we need is a stopwatch program. Introduce the time command. So, in the nick of time. So, all you have to do to time a program... Let me get out of this. Bloop. There we go. Documents. HTOP1XC3. There we go. Say... I'll go to labs. I think lab 6. Yeah, Solitaire. So, Solitaire is a program that I gave my 2 MP3 students as a final exam question last year. So all you have to do is time, execute Solitaire. So this is like a little game. It's a peg solitaire game. This is actually used in Lab 6, but all you do is you sort of move the pegs around, and the object of the game is to try to eliminate all of the pegs on the board by jumping. You jump a peg and it removes a peg, just like in checkers. But anyway, so once you have terminated the solitaire game, once you've terminated the program that you're timing, you'll get statistics. So, real time. So you get real time, user time, and system time. Real time is it's just the time difference between when you started the program and when the program finished, right? So that's the amount of time that the program was running, raw. The user time is the amount of time that the program spent executing user code. User code means the code that you write, in addition to libraries that your code calls, right? And then you have system, which is system mode code, which is system calls and kernel type stuff. So the kernel stuff, generally speaking, runs very quickly and doesn't require a lot of time. The user mode code requires, more time. So you can see, in this particular instance, I played solitaire for 26.5 seconds. But of those 26.5 seconds, only 0.003 seconds were spent actually executing code. The entire rest of the time, it was waiting for me to give it input. Right? So, yeah. So this is cool. Time is a really useful... It's a really useful command, and it's kind of your... It's like the perfect... It's the perfect... It's the perfect middle ground between getting results quickly and easily and those results being detailed. It's like literally taking a stopwatch to your programs, right? And those results are actually functionally useful. So, you can also use the GNU version of time and track memory usage as well. So, there's a problem, not such a problem. Like, Bash has its own version of time that it prefers. Like, it defaults to its own defined version of time. But there's another time program that's stored in user/bin. So user/bin/time. There we go. If you activate verbose mode, and then you execute solitaire, then, you can play your solitaire game a little bit more. FP, IK, PP, etc. So, when you terminate the game now, using the GNU version, which is like the more standard Linux version, like, it's an older version, I think, than the version in Bash, but I could be wrong about that. So, it reports user time and system time, of course. Percent of CPU this job got. Elapsed wall clock time. So I spent 16 seconds in that game. That's the real time, right? Now, the interesting one is maximum resident set size. Maximum resident set size in kilobytes, that's the amount of memory that this process was allocated by the operating system. It's not how much memory it used. It's the size of the chunk of memory that the process was given. Generally speaking, unless your program goes over a certain baseline memory usage, you're not going to exceed. It's improbable that any program that you write for me is going to need more than 1.5 megabytes of memory. Because a megabyte is 1,000,000 bytes, right? And an integer is 4 bytes, so you would need 250,000 integers, roughly speaking, to exceed 1 megabyte, and we're talking about 1.5 megabytes. So anyway, that's how much memory your program is being allocated by the operating system. So we can use time to produce a rough estimate of memory usage, which is good and cool, because memory usage, like, for a number of reasons, memory usage is much more difficult than time usage. For time usage, all you're really doing is, including some metadata about when the clock's ticking. What the start and stop times of, functions and algorithms are. Memory usage, it's like, because the memory management system is much more complex than time itself, it's much more complex to get a good reading of how much memory your program is using. But, the amount that the amount that the operating system allocates it, that will increase if it exceeds this baseline level. So that's a good indication if you're using a lot of memory, if you're a memory hog. So, good. The other thing that's interesting is it reports the exit status. So, we haven't really gotten into exit statuses very much so far. Exit status is, when you write a C program, and at the end of the C program you write return 0? What that actually is doing is that's returning an exit status of 0 to the shell, right? The return value of any C program ends up in the shell. Bash, or if you're in a shell script inside of the shell script, you can actually read the exit status of the programs and commands that you execute inside of the shell and use those to do things like decide program paths inside of a shell script. So you can use the return status of your program in order to select one or another option inside of a shell script. That's extremely useful. But yeah, so non-zero statuses indicate an abnormal exit. So it's useful to have a program that'll report the exit status to you. While time gives you a quick rough idea of how many resources your program is using, you'll often need more detail than this. So let's talk optimization. I'm gonna let you guys read that, but that's a neat little chart done by the XKCD people. How much time you can afford making your tasks more efficient before you're spending more time than you save. So if you, for example, if you can do something that shaves 1 minute off of something you have to do daily, then you are justified spending an entire day doing that. And after 5 years, you'll be making time back. Or, depending on how much time you spend. So, introducing gprof. Not me, prof. gprof. The GNU profiling utility. HTOP gives us a good idea of our system load, and time is good for fast estimations of runtime and memory usage, but these programs do not tell us anything about our program's structure. All of the tools that we've been discussing so far take a black box perspective, right? They're not analyzing the internal details of our algorithms. gprof analyzes the internal details of our algorithms. So this is white box analysis, not black box analysis. Profiling lets us break down our program's structure and view statistics about the use of individual functions. This information can be used to help us optimize our programs. So, what it does is it analyzes all of the functions, and it says, okay, you spent this much time in this function, you had this many executions, this function called this one, and this one. It's like it breaks down the structure of your program. Profiling doesn't tell you how to optimize, but it does tell you where to optimize. So if you have a function which, is using up a lot of time or is executed many, many, many times, any optimization that you find inside of any optimization that you make inside of a function, the amount that optimization, the amount of that optimization is multiplied by the number of times the function is executed, right? If you've saved, 0.2 seconds, but the thing's run 10,000 times, how much time are you saving, right? 0.2 seconds times 10,000. So, before we get there, though, let's talk about optimization. Autobots optimize. Before we profile our code, let's learn a little bit about GCC's automatic optimization flags. Ho ho yes! GCC can perform automatic optimizations for you. I bet you didn't know that. So, basically, you've got various O levels. Just O is standard optimization. Then you've got levels 2 and 3 optimization. You also have size optimization, which reduces the size of the actual C code as far down as possible. So it's optimizing for shortening the program itself. This is the type of optimization that you would want to use if you had extreme memory constraints, like old Game Boy type memory constraints. Like having to increase the pixel size on the back sprites of the Pokemon for the first Pokemon games. Optimization levels. That's where we're talking. O fast is speed optimization. So optimize me for the fastest possible execution time. And OG is debuggability optimization. So, and that will only make sense once we talk about the trade-offs a little bit. So, optimization, these optimizers, actually rearrange your source code. These are source code transformations. It's not magic. They're just identifying common patterns and swapping them for different patterns which do the same thing but are more optimal, right? And like years and years and paper upon paper upon paper of research has gone into these guys. So you can be sure that these optimizations are, like, this is some of the best work that computer scientists have done in optimizing GCC. Like, I think, like, one of the only other, like, Haskell has some really, really, really good optimizations too. Like, that's one of the reasons why Haskell is liked so much by all of the professors and hated so much by all the students. One of the reasons professors like Haskell so much, it's not just that the semantic is so elegant, although that definitely helps. It's also that the compiler itself, like GHC, is an extremely good compiler. Like, the smartest people in the world have put that compiler together. You can rely on it. But anyway, so the problem with your source code being rearranged like this is that it makes it more difficult to debug. The whole debugging process, in general, relies on you having knowledge of the structure of your program. The more the structure of your program is mutated to produce more optimal results by the compiler automatically, the harder it will be for you to be able to find bugs in your program. So we have this special optimization level, debuggability optimization, which basically performs a subset of the optimizations available, which are minimally invasive and do not alter the source code too much, so that you can, you can still get meaningful debugging results. In general, though, optimization is the final step. It is the last time that your code gets compiled before you release it out into the world. You should perform optimized compilation on it. So, yeah, like production version, right? Your distribution version of your code should have the optimization used on it. So the other thing about optimization is that it takes time. GCC executes quickly. GCC at 03 optimization level does not. Like, let's take a look here. So GCC, let's actually time it. So time GCC I just do solitaire.c. So regular, it takes 62 seconds of user time. Level 1 optimization. Haha. Ignoring return value of scanf. You see? So at level 1 optimization, we've doubled our compile time. How about level 2? It increased the compile time again. Level 3, you can see level 3 optimization, we're now taking, 5 times as long. And it's not, it's not that big a deal when it's still a fraction of a second. But, imagine if it took 10 minutes to compile your code, right? Level 3 optimization would take close to an hour. So, yeah. So, any questions so far? I'd like to take a moment, see if you guys are still with me. Give me a thumbs up if you guys are still with me. The few, the proud, the 12. I'm still running, right? Yep. Thumbs up. All right. Wonderful. So, this stuff isn't like... This isn't that bad. It's just a matter of knowing what these tools are and what they do. So you can use these levels of optimization on any program you make. Yes! You can use them on C... You can use these levels of optimization on any C program. Because they're native to the GCC compiler, right? However, if you're at any point in the future writing a C++ program, it is probable that they have similar attributes for the C++ compiler that operates inside of GCC. So GCC stands for the GNU Compiler Collection, right? So it includes C, it includes C++, but in order to actually compile C++ code, you don't use GCC, you use G++, and then you compile your code. But G++ probably has a number of optimizations as well. G++. Yeah, it just redirects to GCC. Yep. So there you go. Anyway. Oh, it even does Objective-C. So let's talk about gprof. Gprof requires code to be inserted into your source files by GCC so it can keep track of things. So in order to do this advanced level of profiling, where we're actually breaking down the structure of the program itself, GCC has to do some code injection. This will, of course, make your code run slightly longer than it would have otherwise, but normally, you wouldn't include gprof flags in like a release version of your code. So, number 1, you compile your code using the PG option. That tells GCC to insert the profiling source code. So once you've done that, the executable that GCC produces will create a file called gmon.out, which anytime it's executed. So So let's do this. We've got gcc-pg solitaire.c out profiled solitaire. There we go. So now I execute profiled solitaire, right? And, you know, I play my little solitaire game. I make a few moves just to give it something to chew on. Okay, there we go. Solitaire terminated. So if I take a look, now I've got a gmon.out file. I then call gprof on gmon.out, not in executable format. Sorry, I forgot we have to capture the output. So gprof gmon.out, save it to results.out or some file name. Ooh, Oh, this is interesting. Oh yeah, because I'm not using it correctly. I'm a dummy. That's the problem. Is I'm stupid. And incidentally, did I run the right solitaire program? Yeah, I did. Okay. I'm stupid. Sorry, guys. You have to... It's gprof, then the name of the executable. Profiled solitaire. That's why it was complaining that it wasn't an executable. And then you do the angle bracket, the greater than sign. That sign means capture the output and write it to a file. Right? So if we just execute this, we just get a bunch of stuff. Right? If we then include the angle brace and write it to log.txt, nothing appears in the terminal. But if we if we go less, what would I call it again? Log.txt. This is the actual file. So it captures the terminal output and it saves it to a file instead of displaying it. It's extremely, extremely useful. You're going to use it in your lab today. So, flat profile. We've got a number of functions. Parse move is one, print board, effect move is valid move. A number of times it's called, and the number of times that are spent in those calls. We also have a call graph, which tells us which functions are calling which other functions. So let's take a look. Here's a different example output. So the thing about this example output, you'll notice all of the time is 0. That's because this isn't a sufficiently complicated program to take more than 0.01 seconds to do anything, except for wait for the slow old prof to do stuff. So here's a different example output from a different function that does actually have something interesting to look at. So you can see we've got calls, we've got milliseconds per call, we've got total milliseconds, cumulative milliseconds, and the percent of the amount of time that was spent in any one of these. So, the flat profile provides information for every function in every function that the program uses, yes, even libraries. So if you're using printf or scanf, it's going to pick these up too. So, percent time, the percentage of total runtime the program spent on each function. Percent time. Cumulative seconds, the number of seconds spent in this function plus all entries above it in the table. So the cumulative seconds is basically this plus this plus this plus this running total going down. Calls is the total number of times this function was called. That might, like, that's one of the most interesting ones for us. Self milliseconds per call, average time spent in this function per call. That's an interesting one as well. And of course, total milliseconds per call, average time spent in this function, and descendants per call. So, this and all of the things that it called. Name is, of course, the name of the function. We then also have the call graph. So in this example, our call graph looks something like this. So main is, of course, main, the main function. Main is calling each one of these, is1, print board, effect move. Effect move calls parse move. Is valid move also calls parse move. So you can see parse move is being called twice consecutively by different functions. Perhaps an optimization that we could make is to parse the move, store the results, and then pass those results to effect move and is valid move, rather than having both of them invoke parse move. These are the types of optimizations that are suggested to one by the call graph. So the call graph gives you an idea of how many times each function is called by every other function in your program. So if you look at these, in any particular entry, you have the calling function, the name of the function being called indented. I guess for you that would be that way. And then a list of all of the functions which are called by the above function. They're referred in this list of functions by number. So main is 2, report is 3, so 3 is 3, that's why it's indented. 4 is called somewhere, I don't know. Lookup is 20, skip space is 44. And another interesting one, when you have recursive functions, the number of recursive calls that a function makes that's indicated with plus and then the number of recursive calls. In addition, it'll tell you how many times out of the total number of times the function was called, it was called from this particular function. So this is, again, very, very useful information for understanding how your program actually operates. Cool. So if we took the entry here, if we took the information here in, this item, and this item, and we produced an actual graph with that information, it would look like this. We've got start calls main calls report calls all these guys. And that's what this, start calls main calls report calls all these guys. That's, it's useful to have this information because this allows you to analyze the structure of how the functions are actually being used as opposed to how you think they're being used. This is an empirical way of actually diagnosing your program structure. We cool? Yeah? Hopefully. Good. Still, yeah, good. So, now that we've talked about gprof and how useful it is, let's dig a little deeper. Deeper still. Yeah, good. So now we know how to profile code at the level of functions. But we can go even deeper than functions. We can profile the code at the level of lines of code themselves. gcov will annotate your source code itself with how often each line of code is executed, what lines of code are actually executed, and how much computer time each section of code requires. So gcov is a different tool. Again, it'll tell you. So rather than like generate a separate report like gprof does, gcov, like when you're talking about annotating, when you're talking about like reporting to the user the number of times any particular line of code is executed, it makes the most sense to annotate the existing source code as opposed to generating a different, separate, independent report, right? But anyway, gcov is fantastic to use in combination with testing because it will tell you whether your tests have full coverage of the source code. That is why gcov is called gcov. The cov stands for coverage. Code coverage testing is a, like, So, when it comes to testing, right? You know, you're writing your tests. Type, write up a test. How do you know if your tests are actually testing your entire program? You can't. Unless you're using some kind, like, either you know because you are so familiar with the program's structure, or you just are guessing, right? You're guessing that you're exercising every piece of code in the entire program, and that's a really, really important thing to test. If there's a bug in a branch of the code that you never tested, that bug is going to go undetected and make it into the release version of your product. Absolutely. It's particularly pernicious when you're talking about interpreted languages like Python, because in Python, you don't even get errors until you try to execute, right? So, unless it's a syntax error that prevents the program from being parsed, you don't get the error until you try to execute the branch. So code coverage is an extremely important thing to be able to test for. And it's fantastic to have a tool that will automatically just tell you if your code is being tested thoroughly or not. So, in order for the results to be meaningful, we can't use compiler optimizations since they change the source code. Yes, so, although, might be interesting if you want to see what the optimizations are doing. But yeah, so let's take a look here. To use gcov, we need once again to perform a special compilation procedure. GCC, fprofile, args, ftest, coverage, and then the name of the file. So, let's try this out. GCC, fprofile, args, ftest, coverage, solitaire.c, out, cov solitaire. Uh-oh. Yes, I did mean coverage. There. Seems I've been lied to. Man, GCC. GCC. Oh, there are your optimization options, by the way. So, one interesting thing that I should note is that there are 50 years worth of accumulated tools for, like, working with programs in these commands, in these compilers that we're learning how to use. We are barely scratching the surface of the types of analyses that you can do. Like, you should not consider gprof and gcov to be the only ways of profiling code. Not even remotely should you think that way. The whole point of this course, like the point of this course in general, is to elaborate to you, put it in your brains, that these types of tools exist and that they have utility, so that no matter what type of program you're making in the future, you know, if it's Python, if it's C, if it's C++, if it's Java, if it's Haskell, if it's OCaml, if it's I was gonna say the one that, like, brain and then F, and if you've heard of this language, you know what I'm talking about. No matter what programming language you're using, you should be looking for these tools. And shell automation and shell scripting is applicable to all of them, as long as you're in a Linux environment. As long as you're in an environment that supports this type of scripting, you can use it to automate and speed up your programming practice. Like, the more you can do with less by making the computer do stuff for you, the more effective a programmer you will be. And the effective programmers are the ones that get hired. So if you are concerned about your future employment, learning how to use the tools that you have available to you effectively is going to be essential. The whole point of this course is to teach you stuff that you will need to, that will be impressive sounding to people that you interview for co-ops. That's the entire point of this course. That, and to teach you C, because it's a prerequisite to something that's coming up later on in the second year. But anyway, let's see if F-profile coverage without the arcs and F-test flags work. So gcov, or what is it, solitaire.c? No, we then have to execute it. Yes. Oh, jeez. All right. Execute the file. Cov solitaire. So fp ik df fp, etc. So now we should have, what is it called? .gcda file. Yeah, there it is. Solitaire.gcda. gcov solitaire.c, creating solitaire.c.cov. .gcov. So let's take a look at it. Hopefully this worked. It did! Hallelujah! 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 So, this is the source code for the Solitaire program. Very, very simple. This is your line. This column is your line number. This column is the number of times the code was executed. If it's got number signs like that, that means this wasn't executed. This is a branch that was skipped. So, you know, obviously me playing the Solitaire game for like 3 or 4 rounds, that's not going to do full code coverage, obviously. Parse move was invoked 10 times. This branch was never executed. This branch was never executed. Like, you can see at a glance what parts of the code were not exercised by the tests that you ran, which is extremely, extremely, extremely useful. Also, you can see that certain parts of the code are executed a large number of times, like the test to see if the board, like, if you've won, like, it has to check every cell in the board to see if it's the winning arrangement, right? So that gets run quite a few times. So yeah, gcov. Tell me that isn't cool. Tell me I'm not blowing your mind right now. Right? And that's simple. That is dead, like, producing those results is dead simple. All you have to do is know that the tool exists and know what command to use to invoke it. Right? That's all you need to know in order to run this very, 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 very useful analysis. This analysis could be, like, you can integrate this into scripts. What does dash colon mean? I think that means, let me take a look. Yeah, that's just, like, that's a line that didn't, like, that's a line that doesn't contain anything to have not executed. Like, no, like, it's a line with no executions, but which didn't need any. Like, it's not being skipped, because it's all stuff like comments and function prototypes and include statements. Like, see anywhere there's a comment, it lines up with a dash, just a hyphen, you know? Things where it's like just a end brace on a line, you know? Yeah. Cool. I think I've got a, so this is another piece of example output. It is execution count, line number, source code. The consecutive octothorpe characters indicate that the line was not executed, i.e. not covered. So, in theory, if you're a person who is employed designing tests for software, which is an entirely possible thing, like, there are software professionals who are employed exclusively testing people's code. Like, this is a thing you can get a job doing. You know, running a gcov analysis will tell you if you need to add test cases to test this, that, or the other, right? So, yeah. Yeah, anyway. So, Unix file permissions. Make me a sandwich. What? Make it yourself. Sudo make me a sandwich. Okay. Unix is basically a simple operating system, but you have to be a genius to understand the simplicity. Dennis Ritchie. Remember Dennis? Good old Dennis, inventor of C? Yeah. Well, inventor of C insofar as we need to pick one person to call the inventor of C. C, of course, was worked on by many people, or a group of people at Bell Labs, but, you know, Dennis is he's our poster boy, in the same way that Linus is our poster boy. Anyway. So let's talk about Unix file permissions. Within the Unix file system, 10 bits are allocated per file to record file permissions and are visible when using ls-l. ls-l. There we go. See these? See these guys? That is your file permissions. Actually, these ones. These are your file permissions. So, the first one is either D for directory or dash for file. D for directory or dash for file. Yep. The next ones are user permissions. That's your permissions. Read, write, and execute. There are 3 groups of read, write, execute permissions for user, group, and others. So let's talk about readability, writability, and executability first. If a file is readable, that means you can open it, you can take a look at the contents. You can copy from that contents, right? If a file is not readable, then you can't read it. Like, you can't access it in any way. Readability is the most basic permission. Most things are readable. Like, the reason that you can look at, the stuff that's in root is because it's readable to user but not writable. Actually, let's take a look at that. cd root ls l lsl. What am I talking about? There we go. Yeah. So. Oh, that's interesting. I can overwrite bin if I want. That's probably not a good idea. So, let's go into bin. And let's take a look at the permissions in here. Yeah. You'll notice that all of these guys are executable, right? So anyway, you've got read permissions, write permissions, and executable permissions. Write permissions should be fairly straightforward. If you have permission to write, that means that you can make modifications and save them. If you do not have permission to write, you can only look. You can look but not touch. And executable permission is, can this file be run as a program or command? We've had to do a little bit so far with changing permissions to executable in order to be able to run our shell script. So let's talk about these user groups. So we've got user, group, and others. In Unix, you've got, I'll just talk about it from this slide, So, user is you. Each file has an owner, and these bits specify the permissions for the owner. This will be you most of the time. So you make a file, you are the user, you are the owner, right? Each file is so if you take a look in your file, in your home directory from like root/home, every user that is a valid user and enrolled user inside of the system will have their own directory inside of home. These are the users, right? When you log in, you are brought to the home directory of your user. When you create a file, that file has your user name attached to it. So there you go. Under Unix, users may be collected into groups for ease of management. Group permissions apply to the group you are a member of, if any. Think of the difference between student and faculty access to something like Avenue or Mosaic. So it's not, I don't believe we're using groups to organize Pascal, but definitely think about Avenue, right? You are a student in Avenue, so you do not have the same ability that I do to, for example, modify how much an assignment is worth in the gradebook, right? Doesn't make sense for you to have the ability to modify how much your assignments are worth, but it does make sense for myself or the TAs. Like, the TAs and myself are all in, like, the instructor group. And if you look on Avenue, we're actually tagged that way in the class list. So, yeah. It's useful to have groups just to, to be able to organize things. So So the question then is, okay, so what group do these permissions apply to then? And the answer is the group that the user is a part of. So each user may only be a member of one group, and that, like, and the group is, or maybe that's not true. No, the group is indicated here. Sorry, never mind, I'm dumb. So the owner and the group is indicated inside the file permissions. So the group that's specified is the group these permissions would apply to. And others is just everybody who's not in the first two categories. People who are not the creator of the file and people who are not in the group that is specified. So, yes. And file type only specifies whether an item is a file or a directory. It's a bird. It's a plane. It's super user. If you're trying to do something in Unix and Linux, Unix/Linux, and you get a permission denied error message, that means that you don't have the correct level of privilege for the operation that you are trying to perform. You are an underprivileged user. At least, well, probably not actually. You probably shouldn't be doing the thing that you're trying to do, unless you're installing software. That's like installing software is pretty much the only time that you should need sudo access under normal circumstances, for a normal user. There is only one way around this problem of having permission be denied you because you don't have the correct level of user privilege. And that is by invoking superuser. You invoke superuser in the same way that you use the time command. You just type sudo, and then you type whatever command that you weren't able to execute before. That's why sudo make me a sandwich works, because superuser do. Sudo stands for superuser do. In Linux, the superuser account, which is called root, is omnipotent, omniscient, and omnipresent. Yes. So root has unrestricted access to all commands, files, directories, and resources, and this also means that the root user has the ability to install programs for all users, change system settings, and compile that kernel. So, superuser can do anything. Another thing that superuser can do is grant and revoke permissions for other users. So somewhere in your operating system, there is a file that specifies which users have sudoing privileges, right? In a place like Pascal, you do not have superuser permissions because we don't want a malicious agent infiltrating Pascal and deleting everybody's homework, which a superuser could totally 100% do. Actually, I don't. Neither myself nor the TAs even have superuser privileges on Pascal. I'm pretty sure. I might be in the sudoers file, but I don't think I am. At any rate, Derek and John and Sebastian, who are the IT people in the cast department, these guys are the guys who have sudoing privileges. Which you guys will have found out from Lab 4, where you were messing around with Bash, right? So, the main difference between having a Linux system or virtual machine and logging into the Pascal server is that you don't have sudo privileges on Pascal for obvious reasons. So, if it's your own home computer, by default, you will have sudoing privileges. On computers where there is only one user, at least one user of any system must have sudoing privileges, right? If there's nobody who has sudoing privileges, then there is nobody who can grant sudoing privileges, which means there's nobody who can grant anybody permission to install anything, which means that you can't install any programs on your computer, which is inherently problematic. So if there's only one user on your system, then you do have sudoing privileges. So, the group scoop. By default, each user is already in a group containing just itself. The group's name is the user's name. So if I take a look at CD Lab 6, yeah, so it says Nick. So it's Nick is my user and Nick is also my group. I am a group containing myself. You can create a group, assuming you have the authority to do so, with group add group name. You can add a user to a group with user add -g username group name. So there you go. Very simple. So how do we modify file permissions? We've talked about file permissions. How do we modify file permissions? This is like a generalization of our discussion of how to make shell scripts executable. So it's chmod, chmod, and then you have, like, the easy way to do it is to use these newfangled tags that they've come out with recently. Not recently, like, I think they're like 20 or 30 years old, but the old way of doing it was by specifying the bits themselves in octal, like these bits in octal. And that was actually one of the few times you would actually, like, that was one of the only times in computing that you would actually run into needing to know what octal was. And since they've added all of these new options to be able to not have to use octal, most people will never see octal again in their lives. But anyway, so if you want, so basically how it works is you specify a person or persons, you specify whether you're granting or revoking, and you specify the permissions you want to grant or revoke. So if I want to take a file like touch my shell script.sh, so that now exists, my shell script.sh. Of course, it's in, it's not executable at the moment. So if I want to make it if I want to make it executable for me, user plus execution my shell script.sh, and I think that'll do that. There we go. Executable permission now enabled. I think if you use A, that's all. Yeah, A is all. So now it's executable for everyone, not just myself. So there you go. U is user, G is group, O is other, plus is grant, minus is revoke, R, W, X, read, write, execute. You can also change ownership with chown. Every file belongs to both an owner and a group. The chown command changes file ownership. So, chown, owner, comma, or owner, colon, group, and then file name. You can change just the owner by not specifying a group, and you can change just the group by not specifying an owner and leaving in the colon. So there you go. Now you know how to use file permissions. Are there any questions? Give me a thumbs up if there are no questions. Good. Awesome. Last slide comic. Sudo SU. SU is super user, by the way. Invoke super. So, sudo invokes super user for one command. SU invokes super user for a session. So like if you have to do several sudoing, like if you have to do several commands which would need super user, you can just call SU, and that puts you in super user mode. But anyway, Rob M is not in the sudo errors file. This incident will be reported. Hey, who does sudo report these incidents to? You know, I've never checked. You're on the naughty list now, boys. So, important instructions. Go to this website and print this tape off and tape it up somewhere in your workspace. Better yet, make your own from the slides and also tape it up in your workspace. So, let me just show you what I'm talking about here. This is what this is it's a Unix/Linux command reference sheet. So it's quick reference for all of the commands, well, most of the commands that we're talking about. I don't think stuff like gcov and gprof are on this, but yeah. You should make one of these for yourselves and just put it somewhere obvious. Like, there are a lot of commands to memorize, and I'm gonna level with you guys. Nobody memorizes all of these commands. Everybody has a sheet like this in their workspace that they refer to as they're working. Like, that's how, practically speaking, this type of stuff works, right? So if you don't like this one, find a different command reference sheet. Doesn't matter which one you use. Again, like, optimally, you would make your own. But yeah, you should have at this point, you should have a reference sheet somewhere posted in your workspace. And then credits. So, all right. That's topic 7, done with 10 minutes to spare. I guess I'll just, the next topic's going to be, it's a little bit on the longer side, so I guess I'll do the first 10 minutes of pointers, and that's where we'll end things. So, pointers. Pointers. I'm going to give you some pointers. Haha! So, T-Rex in programming advice. Are you having trouble programming your computer? Let me give you a few pointers. Ooh, ouch. Was that a bad pun? It was a indirect reference? I suspect that all these are bad puns. Don't worry, they're the least significant bit of my speech. Oh-ho. Jokes explained. Aren't pointers programming tools, T-Rex? They are. They allow one to reference the address of data instead of the data itself. It's like how knowing someone's phone number lets you get in touch with them personally. Hence the delightful indirect reference pun. I too think these puns are pretty awful. Conclusion. Everyone, program harder. I agree with T-Rex in this instance. So, when a wise man points at the moon, the imbecile examines the finger. By a person a lot of quotes get attributed to. So, what the heck's a pointer and why should I care? Pointers are one of the most powerful constructs in C. A pointer is a variable whose value is a memory address. Where most variables directly reference the value stored at some position in memory, pointers are indirect references. In this set of slides, we're going to talk about pointer data types, pointer operations, and applications of pointers. So, pointerization. A pointer is not declared as a new data type, but as a modifier to an existing data type. So let me just get back to where you once belonged. Bam, bam. Get back to where you once belonged. So, that's not where I'm keeping stuff. It was in CD tab code. Make directory. Topic 7. 8. This is topic 8. CD topic 8. Alright. Get it. Pointers.c. Alright. Include. Standard io.h. Int main. So, there we go. So we've got an integer. Integer x. Value is 6. We have an integer x pointer. It is useful to include the term pointer in the name of the variable. So, the pointer, what makes it a pointer is the fact that it has a little star by it. The asterisk pointerizes the variable. It doesn't actually matter for if you only have one, whether you put it here, but let's group it with the data type because that makes more conceptual sense. This is a integer pointer. X pointer is an integer pointer. So pointers have a data type attached to them, right? So it's not just I'm pointing to a memory address. I am pointing to the memory address of an integer, right? So the star character indicates that pointer is an integer pointer. This is to say, pointer points to a segment of memory the size of an integer. The star character may be applied to either the data type or the identifier itself. If you include it, so if you have a list of multiple things you're declaring in one line, the star only pointerizes the one that it's closest to. So if you wanted count pointer and count both to be pointers, you'd have to include another star here. But that's fine. That's beside the point. So, in blue Blockovision, if we have an integer and we have a pointer, it points to that integer, but not by default. We have to set it up to do that. The way that we do that, I will answer that question later. The answer is no. I didn't hear about that. I didn't hear about the AI that GitHub is trying to make. Like, is GitHub the company trying to make it, or are people's efforts on GitHub to make an AI? So, printf x equals whatever the value of x is. Printf x pointer equals. So the way that you print a pointer is using %p. The way that you access the address of something is using the ampersand operator. This is the ampersand address of operator. So this means the memory address of x. So let's compile that code. Topic 8, what did I call it? Pointers. GCC pointers.c. I need a semicolon. There we go. A dot out. I should include new line characters. Gets me every time. Bloop. Recompile. There we go. So, x is 6. X pointer is this memory address. Good. If I want to access the item at that memory address, I have to dereference the pointer. So x value at x pointer is going to be an integer. The way that you get it is by, again, using the star character. It's a little confusing because it has a different meaning here than it does here. This is pointer dereferencing. This is pointer declaration. So that's a little confusing, but value at x pointer is 6. So you can access the thing at the pointer, at the location the pointer is pointing to, by using the dereferencing operator. So, since pointers are more direct manipulation, or are a more direct manipulation of memory, you can squeeze some efficiencies by squeezing in some pointers. So, because you're doing the memory management and you're always going to be more efficient than any computer that does memory management for you, you can produce more efficient programs by manipulating your own pointers. Stylistic points. To avoid the confusion on the previous slide, it is better to declare pointers and direct variables on separate lines. Putting some indication that a variable is a pointer in the identifier is a good way to be able to tell which variables are pointers later on. Highly, highly recommend putting like PTR somewhere either at the beginning or the end of every pointer you make, unless it's an array. But anyway, I think we shall, we'll call it there. Tomorrow we will continue talking about pointers. Let me just see what we got going on here. Boop. Boop. Oh, they're just not going to work for me, huh? Okay. So, GitHub is making an AI that will help you program and even make a program with a description of the program's function. Yeah, so whenever I hear anything like this, I'm just like instantly extremely skeptical, because the problem, like this is by no means a new idea, right? This idea that you could generate that you could generate programs from high-level descriptions of the programs. This is in no way a new idea. They've been trying to make this work for a very long time. Can I go to the code? Yeah, I can go to the code. Yeah, I can go to the code. Here you go. Yeah. This is in no way a new thing. They've been trying to get this to work for years and years and years. And the fact that they're calling it AI or applying machine learning to it or something is not going to change the fundamental fact that in order to describe a program in sufficient detail for a computer to be able to produce that program as a functional program that does what you want it to, you have to specify that program in sufficient detail that you might as well be programming it anyway. So no, I'm a bit skeptical. Yeah. Yeah, no. Nah. Nope. Skepticism is your professor. Especially if they expect this to work with natural language descriptions. Like, yeah, that might be like the thing that they're doing is like they're trying to use AI to be able to parse natural language descriptions and produce like the types of descriptions that would be necessary for program generation. But yeah, no, it, like, don't get me wrong, I'm not saying they shouldn't be trying, right? It's just like, I don't know, like, as an educator, I have a problem sometimes with people who are like, you know, oh, I won't have to learn how to touch type because in the future, computers will just be able to read my mind and I won't have to use my hands. and all kinds of ridiculous nonsense like that. And I speak as experience. I speak from the experience of a person who was ruined by calculators in elementary school. Like I was really good at math, and then I got a calculator, and now I'm terrible at math. So, it's like I know, like, I don't know. I just have, like, sometimes when people talk about that kind of stuff, they're like, "Oh, well, I won't have to program in the future because computers are just gonna do all my programming for me." It's like, nope, 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 nope. The correct way to view any program that is produced by human beings is as a tool, right? A tool that requires skill to operate, right? People like, anyway, I'm just gonna rant about this. But anyway, we'll leave it there for today. Talk to you guys tomorrow. We'll talk more about pointers. Enjoy the lab today. Hopefully you guys enjoy the lab. Hopefully you enjoy the lab tomorrow as well. I think the labs are enjoyable, but then again, I'm not a student. So, I had fun putting the labs together. Mark helped out quite a lot on Lab 5, but yeah. Helped out quite a lot. He was basically, he wrote it with my direction, and then I edited it, and that was it. So, there you go. Anyway, take her easy, folks. Keep it chill. Keep it happening. Stay on the download. Stay on the upload. All that internet slang. Man. What the heck is going on?